Hello everyone, I'm Xiang. Today, I'll make a simple introduction about my current study, especially thanks to Haiyan. As you can see that my topic is partially observable Markov decision process for diabetes measurement with missing data of blood glucose. In the following time, I'll introduce from 5 parts. According to WHO report, there are 422 million adults suffering from diabetes. What's worse is the number still increases. Moreover, a large number of people die from diabetes and high blood glucose. The main cause is they don't manage and control blood glucose efficiently. Besides, in the medical follow-up experiment, they drop out from the experiment, resulting data missing. So this study is devoted to making dynamic treatment plan with missing data for diabetes. It has both theoretical and practical significance, such as solving pure MDP with missing data and help diabetes to control blood glucose immediately. Based on the introduction, the issues to be solved include the following 3 parts. The first one is how to improve the missing data, and the second one is data is often collected with time granularity, such as quarter an hour or half an hour. Whether is the result different or same by using pure MDP model in both cases. The last one is how to use pure MDP model to provide medical decision making for patients with missing data. The figure 1 is a framework of the whole study about solving pure MDP with adjusted MH algorithm. The left part is adjusted MH algorithm. The initial data is the blood glucose data, and if the data is complete, it will be used as observation directly, and if the data is incomplete, it will be imputed by the MH algorithm. And the right part is pure MDP model, which is represented as a 7 tuple. In this study, the way to solve pure MDP is pure MDP package in R. Firstly, I'll introduce the model. Pure MDP model is represented by a 7 tuple. S means a set of states. A means a finite set of actions. P means a state transition matrix. R means a reward, and Y means a set of observations. K means conditional of the observable probability, and gamma means a discount factor, which belongs to between 0 and 1. The left figure describes changes from t to time t plus 1. At time t, the agent state is st, and it can obtain reward rt when taking action at, and at time t plus 1, in the state becomes st plus 1, and the observation which can be observed is ot plus 1. In pure MDP model, there is an important variable, belief. It is a sufficient statistic, that is to say, just needs the current belief but not other information when making decisions. The calculating process is as following formula. When given policy pi, the optimal value function is as follows. Figure 3 is a framework that shows the diabetes measurement process by using a pure MDP model with missing data. The observation YT refers to the blood glucose levels but with missing records. The blood glucose levels are divided into 4 intervals. The observations in these intervals are denoted as Y1 to Y2, Y3, and Y4. For example, the observed blood glucose value is 12.88 at t equals 0, and the corresponding observation takes Y3. When considering missing values, the observation Y refers to the blood glucose value. The state ST indicates the health status of the patient, which is determined by patient's blood glucose levels and sometimes with other abnormal symptoms. The action AT represents the injection of insulin. After taking the medicine, the patient's symptoms change, and the reward RT is used to measure the improvement of the patient's health status. For example, 1 indicates that the health becomes better, 0 means no improvement, and -1 means worse. As the next step T+1, physicians can understand the therapeutic effect of the treatment plan through the changes of the blood glucose levels and dynamically adjust the treatment plan for the patients. So next time, I'll introduce how to solve the issue of missing data. The missing data will be imputed by adjusted algorithm. MH sampling is the abbreviation of metropolis Hastings sampling. But in my study, I make some adjustments about MH algorithm as follows. The first step is to input some data, including translation matrix Q and the probability density of the remaining data after removing the missing Fy and the observation set Y. And then from t equals 1 to n, judge whether the data is missing at time t+1. If the data is not missing, y apostrophe t+1 equals yt+1. But if the data is missing, we will sample yt+1 from yt plus a uniform distribution number between -1 and 1, and sampling u from uniform distribution between 0 and 1. We can calculate alpha as a formula. And then the last step is to compare u with alpha. If u is less than alpha, we will accept the transition, and that is to say y apostrophe t+1 equals yt+1, and else the transition will be declined, and that is y apostrophe t+1 equals yt. And finally, we can get a set of samples. I also use R-code to simulate. The figure 4 is result. From the picture, we can see that the left part is the original data with different proportions of incompleteness. And the right part is imputation data by MH. To compare results, the mean imputation is used. That is to input the missing data by mean. At the same time, use mean squared imputation error to compare the effect between two methods. The formula is processing of calculating. Y means the original data and yi means the imputed data. In table 1, the row is different time granularity and the column is different proportions of incompleteness. The values are average of MSIE of two methods. The red values are MH imputation and the black values are mean imputation. And figure 5 is box plot of comparison results of mean square imputation error with various proportions of incompleteness between mean imputation and MH imputation. The implication is that the larger the missing ratio, the larger the mean square imputation error, and the average values of MSIE of the MH imputation are less than those with the mean imputation. In my study, the state is divided into 4 levels according to blood glucose. The action is divided into 4 levels according to dose of drugs. Considering the data granularity, the state transition process can be divided into 2 versions, long-term and short-term. In the short term, the state transition only occurs between adjacent or same states, and in the long-term version, the state transition can occur between any 2 states. Table 3 is the reward of functions and states for both versions, and the values represent the reward of patients moving to the next state after injection. The lower the blood glucose in the next state, the higher the return, the better the effect. The figure 7 is a visualization of the policy graph in the case of short term, and the figure 8 is long term. The coloring each circle is the probability of patient state, and the arrow is state transition. And the initial belief is the initial belief as starting point, and the label on the arrow is observation. Error rate is used to validate the efficiency of the proposed method. The error rate of actions are measured by number W actions divide number actions, and the number W actions is the number of the wrong decisions using the missing data, and the number actions is the number of actions using the complete data. Figure 9 shows the error rate of action selection when making dynamic treatment plan according to the data imputed by the 2 methods. It can be seen from the figure that there are fewer errors in the action sequence imputed by MH. The contributions of study focus on 4 parts, such as providing a method for recommending actions with the optimal level of drug injection dose, an efficient tool for making decisions with missing data and blood glucose, and so on. However, there are also some limitations to be continued. Thanks for your listening. That's all of my report.